Propositional equivalences definition. A proposition made up of the propositions P, Q, and so on R using some of the operators is called a compound proposition. We say that two compound propositions P and Q are logically equivalent and write P equivalent to Q, provided that P and Q take equal truth values for any given truth values of the variables P, Q, and so on R. In this example, we'll show that the negation of if P then Q is equivalent to P and not Q. First, we count the number of variables involved, P and Q only, so two variables. We write a column for P, a column for Q, and then each possible combinations of truth values. Because we have two variables, we have 2 squared, which is 4 rows, 4 possible combinations of truth values. And we put them in standard order, 2 T's, 2 F's for P, TF, TF for Q. Then we put a column for the expression in this parenthesis, if P then Q. This is just the definition of the conditional proposition. And then its negation, which is the left-hand side of the equivalence that we want to prove. T here, the negation of T is F, and so on. Then we do the same for the right-hand side. The same truth values for P and Q in standard order. Then we have not Q first. The negation of Q is here. And then we can write a column for the right-hand side. Conjunction of P, so this column, and not Q, this column. True and false is false, true and true is true, false and false is false, false and true is false. And then we compare the column on the left-hand side and the column of the right-hand side. Because they are the same, we conclude that the expressions, the compound propositions, that these two compound propositions are equivalent. Similarly, we can prove all these equivalences that are stated here. If we have 3 variables, then the table will contain 2 cubed, 8 rows. And these are the laws that are given in the book. They can be proved the same way. So we assume that we have already proved them and we can use them. But everybody should be able to prove any one of these given laws.